Oh, hey! Didn't see you there. Let's roll the intro. Agent function, your mission, should you choose to accept it, is to explain the unit circle to a bunch of future ninth grade students. Remember, your grade counts on this. This tape will self-destruct in 5 seconds. What do you mean what do you mean we don't have the VFX money for that? Of course we do. They pay us for that. Well, okay, so, just pretend like it explodes, okay?
Today's topic is the unit circle. So what is the unit circle? The unit circle, very simply, is a circle that is centered at the origin and has a radius of 1, something like this.
What is the point of this unit circle? It's very simple. All it is, circle, radius 1, center at origin. I can draw this any day of week. Even babushka, bedridden and crippled, she can draw this any day of week too. So what is the point of this unit circle?
Well, that's a great question. The unit circle actually allows us to do many things. For example, it allows us to see what happens if we break 90 degrees with trigonometric functions, and it also lets us show a lot of new identities that exist between the different trigonometric functions. Now that we learned all this, let's go talk to everyone's favorite two-dimensional Marton to learn more. Hey, I'm two-dimensional Marton. Let's continue with our unit circle. So, this is our lovely unit circle diagram. We've already talked about this. With our radius of 1 centered at the origin, we've got this covered. Now, let's move on to drawing an arbitrary line to any point on this unit circle from the center of the circle. We know that that length is going to be 1 because it's a radius of the circle, and the radius of the unit circle is given as 1. Drawing an altitude, we can create a right triangle. This right triangle is going to be critical. Also, labeling this angle here as currently just x degrees will be very important. Now, we have to remember our SO, CA, and TOA. In this case, the so sine equals opposite over hypotenuse, and cosine equals adjacent over hypotenuse are going to be important. So, if we look at this right triangle again, what we can decipher is that sine of x degrees is going to be equivalent to opposite over hypotenuse, but the hypotenuse is equivalent to 1. Therefore, we know that opposite is simply equivalent to sine of x degrees. Therefore, this side length is simply sine of x degrees. Now, let's look at this green side length that I've just drawn in. Cosine of x degrees is equivalent to adjacent over hypotenuse. Therefore, since the hypotenuse once again is 1, and by much the same logic, we know that cosine of x degrees is equivalent to this side length here, the adjacent one. This is a very important step, because now if we look at this point here, right, we know that it's composed of the x value away from the origin as this green side length, and the y value is equivalent to this blue side length as drawn here. Therefore, we know that this point is always going to be equivalent to cosine of x degrees, comma, sine of x degrees. So, this point is very important, because given any angle value, we know that the point in which that angle value will intersect the unit circle is cosine of x degrees and sine of x degrees. Now we're going to get a little bit more technical, so it's important to get rid of the boring stuff first, which in this case is learning some terms. The unit circle we've already covered to death, so that one's all good. However, theta is something that I will be using in the following examples. Theta is when you have an unknown angle. It's very similar to a variable like x, however, is more commonly used when dealing with angles. Our initial ray is this line here, which is drawn in the positive x direction. And from that, we also have our terminal ray, which is our final value, which is always the initial ray offsetted by a certain amount of degrees. In this case, we have theta degrees. When you offset the initial ray by theta degrees, assuming theta is a positive number, it'll be going in the counterclockwise direction. If it is a negative number, it'll be going in the clockwise direction. So once again, if it is positive, counterclockwise, negative, clockwise. So, using this new terminology, we can say the intersection of the terminal ray with the unit circle is always going to be equivalent to cosine of theta degrees, comma, sine of theta degrees. Cool. Now, here's another question that I hinted at that we can solve using the unit circle. Theta being greater than 90 degrees. Well, this is very possible because we can look at this amazing point that we already learned about. And we can notice that the cosine of theta component is kind of similar to like an x component, and the sine of theta is very similar to a y component. So we can look at these examples here: sine of theta degrees, sine of 180 degrees, cosine of 0 degrees, and cosine of 180 degrees. These would be things that we usually would not be able to easily solve without the unit circle. That's what the unit circle allows us to do, is it allows us to easily visualize what happens with these sine and cosine and tangent functions when we go over 90 degrees. So if we look here at our cosine of 0 degrees and our cosine of 180 degrees, we can see their corresponding terminal rays. So here's cosine 0 degrees and here's cosine 180 degrees. So far, so good. So now if we look at what's important to notice is our x component of both of these cases. So what is the x component for the cosine of 0 case? Well, we can see that from the origin it goes to 1. So therefore this one's going to be 1. And at our cosine 180 degrees, it's negative 1 is the x component, as you can see here. Once again, with sine, we see much the same. However, looking at the y value of the terminal ray. So if we look at the y value of this terminal ray, sine equals 0 degrees, sine 0 degrees, we notice that it's on the x-axis, which would make it 0. If we look at sine 180 degrees, that is also equivalent to 0. Therefore, once again, remembering our y component of the terminal rays, we get 0 and 0, and this just shows how easy it is to now exceed these values and to understand. So we could theoretically draw any terminal ray anywhere in any quadrant up to 360 degrees and even exceeding it, and we can easily understand why those values came to be. If we look here again, right, and we assume that our theta is equivalent to 138 degrees, right, sine of 138 degrees is going to be equivalent to 0.669, right, and sine of 42 is also equivalent to 0.669. How is this possible? Because you've never up to this point noticed that two sine values or cosine values could be equivalent to the same thing. Well, skeptical Steve certainly doesn't like this. He's asking, what does it mean? Well, we need to learn a bit about Skeptical Steve, right? Just as a little side tangent here. Skeptical, or Skeppy Steve, right? He was born May 12, 2012, and I just want to point out the sheer humanity of this guy. He believes that the Earth is round. Everyone knows the Earth is flat, right? Like, two-dimensional Marton. Obviously the Earth is flat. Anyways, and he also uses light mode on all of his browsers and applications. Like, what a sinner. Anyways, let's continue. So we need to look at this case here, right? So we have our 42 degrees, right? And we noted that theta is 138, right? But 138 is also 42 less from 180. So once again, look, if we look at this here, this would be our 138 degrees, right? This is our 180, but if we draw our two equal 42 degree marks, right? What we notice is that the y value is actually the same. This explains why the two sine values for both 42 degrees and 138 degrees is actually the same in this specific case. It's because if we draw this line here, you can see that they intersect both of those points. And that means that both of the sine values for those two angle measures is the exact same. Also, this face here is pretty cool in the previous diagram. This means that we can really squish down or extend this to any specific point, to any specific angle value, as long as you can see that that the two angle values are equivalent to like theta and then 180 minus theta, as you can see here, because this y value is the same. This only applies for sine. We'll talk about cosine in a little bit here, but you can see that the two y values is the same. I'm really stressing that because that's what's important to notice here. And we can learn the first one of our important trig identities. I'll get to those later. However, we can notice that sine of theta is equivalent to sine 180 minus theta, as we can see in this diagram here. So far, this is pretty groovy, but what would happen if we want to deal with something like let's say if we'd want to deal with another one of these trigonometric identities. So let's look at this one. This one's a little bit more difficult to notice. However, once again, we're looking at the y values. Here's one of our terminal rays, and here's another one of our terminal rays, right? So this is equivalent to theta degrees, and this is equivalent to theta degrees. If we look at this is kind of just a rotated picture of what I showed earlier. So this would be 360 degrees, a full circle, right? And then this portion here would be 360 minus theta degrees. So if we look at our y values for both of for the terminal rays here, right? What we can notice is the fact that our terminal ray, this one, is equivalent to this one. However, in the fact that this one has a positive y value and this one is a negative y value, but they are in fact the same y values. So we can now learn that sine of theta is equivalent to negative sine 360 minus theta. These would be considered what we call trig identities. So it's kind of like we have our sine, cosine, theta sitting in a bar, and they meet duplicates of themselves, right? And what they note is how what the input into their functions, which would be the like 180 minus theta or the theta in this case, differ by a specific amount. However, their final values become the same. That's why they're absolute duplicates of themselves. So if we look at cosine, we know that if we use the same logic as previously, right, the 180 minus situation where we have our 42 and then our 42 away from a full 180 degrees, right, what we notice is that unlike sine, those two are not equivalent because we're looking at the x value. However, we do notice something like with the 360 case, because what we notice here is how the x value for this portion here is equivalent to the distance from the y-axis is the same for both, meaning that the negative of this value is equivalent to this value. So they're basically just the flipped sign of the other one. So like, if this value would be equal to 0.5, this one's negative 0.5 here, because they're both exactly 0.5 away from the origin, or the y-axis. In this case, that would be cosine of theta is equivalent to negative cosine 180 minus theta. If we look at another case, right, we can look at the other one that we found is that cosine is equivalent to cosine 360 minus theta. Well, why is this? Well, once again, the x values of these terminal rays are going to be the same, as you can see here. If we look at this diagram, of course, they're both the same distance away from the y-axis, right? And they're both the same positive away from the y-axis. We can also rephrase this in a different way, where we know that cosine of theta is equivalent to cosine of negative theta. Because once again, if we talked about how the way that the the terminal rays work is we know that if we have a positive theta value, it would go counterclockwise, and then a negative theta value goes clockwise. So that's why we can say this one here. So Professor Pete noted that we forgot one trigonometric identity, and that's very important because look, if we draw this line here, right, it doesn't matter if we're dealing with sine or cosine at the moment, we can just go around again, right, and we have another line, but that's clearly the same because, we just went another 360 degrees, right, and the y component and the x component are still the same. Well, if we go another 360 degrees, right, look, we're still at the same thing. This means that both the sine and the cosine functions are simply, so sine of theta is equivalent to 360 plus theta, and cosine theta is equivalent to cosine 360 plus theta. This basically simply means that if that they repeat every 360 degrees. This is why they're called periodic functions. However, that's a topic for another day. So, now that we've learned all of these trigonometric identities and relationships between the sine functions, what we can learn here is that sine of 45 degrees is going to be equivalent to sine of 135 because of what we talked, the 180 minus theta rule. And then we can add this one, we can sine of 405 degrees. We know is going to be the same as sine of 45 because it's simply 360 more than that. And this sine 495 degrees is just a combination of the first two methods in which we went around a full circle, so to 360 degrees, and then we found 180 minus theta on top of that, which got us 495 degrees. And this one's technically a bonus one, however it's a little bit convoluted. Negative sine of negative 45 degrees would also work here. And there's way more examples. There's unlimited, really. Once again, if we look at cosine ones, right, cosine 45 is going to be equivalent to cosine 315 because we know that cosine theta is going to be equivalent to cosine 360 degrees minus theta. And then if we take our 45 and then add 360 to it, we know that that's going to be 405, so those two work. And much like what I did before, if we combine the first two methods, cosine theta is equivalent to cosine 360 degrees minus theta, we get the 645 as well by simply just adding, we could also get that by just adding 360 to this value here. And we also know that cosine 45 is going to be equivalent to cosine negative 45. And these two values are also the exact same. Cosine 315 is equivalent to cosine negative 45. Now, let's go back to three-dimensional Marton.
Thank you, two-dimensional Marton. You're always one of my best friends. Anyways, just to summarize, the unit circle can be helpful in many different scenarios, and we just covered the surface of what we can do with it. This leads into many different things, such as periodic functions, and all sorts of other examples. So, in the end, just to summarize, the two main points that we covered is what we can do when we break 90 degrees, and we looked into some of the basic relationships that exist between the trigonometric functions, some that would not have been as obvious without the help of our lovely friend, the unit circle.